Hi, this is my video for biochemistry, and this is just a step-by-step walkthrough of deriving the Michaelis-Menten equation. So you can see up here at the top, this is actually ultimately where we're trying to get. And what was already given and what we're starting with is reactions here. In the first reaction, you see where an enzyme and a substrate are reacting to form the enzyme substrate complex. And then in the second reaction, where the enzyme substrate complex is reacting to form the enzyme and the product. For the first reaction, there are two rate constants for the forward reaction K1 forming the enzyme ES, I'm going to say because that's easier going forward. And then the backwards reaction K -1 for ES forming enzyme plus substrate. For the second reaction, you have ES, the rate constant K2, and the formation of the enzyme and product. And this is just a forward reaction. This would be early enough in time that there would be so little product that the backwards reaction is negligible and not. And then this just shows the addition of these together, forming the substrate, forming the product of these two reactions. So then we go on to where we started with the instantaneous rate of change. And this is for ES. You'll see it's equal to 0. And that's basically the sum of what's forming ES with what's actually consuming ES. So you can see for the forward reaction, you have K1 times E times S. And then subtracting the reactions that are consuming ES, which is K -1 when ES is becoming enzyme and substrate. And then subtracting K2 times ES from this second reaction here. And you set that all to 0. This is assuming the steady state approximation, which is why we set that to 0. And then over here, this is just showing how to get the total enzyme, or ET, then that would be equal to the unbounded and bounded enzyme. So you see concentration of E plus concentration of ES. And then to get just E by itself, that would be equal to the total concentration of enzyme minus the concentration of the bounded enzyme. So now we'll start off with substituting this expression for E into the expression that we have here. So this will be 0 equals, then we have K1 times concentration, or ET, let's just say, because it's easier, minus ES times S, and then minus K to the -1 times ES minus K2 ES. Ran out of space there a little. Okay. So the next thing that we want to do is we're trying to solve for ES. So we want to get ES on the left-hand side by itself. So the first step to do that, then we would get ES times K1 times S plus K to the -1 plus K2. And that is going to be equal to K1 times E total times S. Okay. And then in the next step, then we are just going to divide by this expression here to get ES by itself. And that would give us ES equals K1 times the total concentration of enzyme times S, and that's over K1 times S, plus K to the negative 1 plus K to the 2. Or K negative 1, not K to the negative 1, or K to the negative. Okay. After this, we're actually going to multiply by the reciprocal of K1. So multiply both the top and the bottom by 1 over K1. And this will cancel out the K1s. And this would leave us with ES is equal to ETS. And then over concentration of S plus K negative 1 plus K2 over K1. And you'll see that this expression here looks kind of familiar from some of what we started with up here. This K to the negative 1 plus K2 over K1 is actually equal to what is called Km, or the Michaelis constant. And Km is actually the concentration of substrate at which the reaction rate is half of the Vmax. So you'll also see by looking at this expression that we have the Vmax is K2 times total concentration of E. So you'll see that here. Okay. So, I'm sorry, I got ahead. We didn't actually get to that part yet. So, now we have for here, we have ES, and what we're looking for is the instantaneous rate of change for the product, which is equal to the Kcat, or K2, which you would see here, the reaction involving the product, be K2. So Kcat times ES. And now that's where we're able to plug in what we found previously for ES. And then when we plug that in, that's where we would get that the velocity equals K2, or Kcat, times ET times S over S plus Km. And this is what would be equal this Kcat times the total concentration, total enzyme concentration, is what is considered the Vmax. So that's how that could be written, and how we get to the velocity here is the Vmax times the concentration of S over Km plus the concentration of S. And basically what the Kcat is the Kcat measures how many molecules an enzyme can actually catalyze per second. And the Vmax measures the enzyme's reaction with the most molecules possible per second. So that's where we end up with this. And to test to also how we said before about how the Km is the concentration of S when the reaction rate is half of the Vmax, you can actually substitute that into this expression here, or you can substitute into this expression here, and you can actually see how the velocity equals the Vmax times S, And then if we have the Km set to be the concentration of the substrate, then you would just basically get the concentration of S times the concentration of S, or S squared. And that would cancel out, and you can see how that would just be over 2. So Vmax over 2 would be when you have the Km. So that was pretty bad, but it was hard to keep track of all the different things and still hold the camera at the same time. But overall, this just shows how to go from our starting expression here and then ending how we derive to get the Michaelis-Menten equation that is up top, which is velocity equals Vmax times concentration of S over Km plus concentration of S. Thanks.